All right. Well, hey, welcome to our last Monday in May. Woo, you can believe it. Um, this month is just cruising right along. So today, what we're going to do is we're actually going to start doing trigonometry. Yeah, I just think it's funny that we're 2 months in and we're going to start doing trigonometry. No, we're actually going to start solving triangles. We're going to start measuring triangles that aren't right triangles, right? We know how to deal with right triangles. We learned about the Pythagorean theorem. The basic trig functions give us relationships between sides and angles, and so we can solve right triangles. But our goal for the next couple days is, what about other triangles that are not right? We call them oblique triangles. But what about those? What about triangles that are not right? Well, we're going to have to develop some new tools, but that's what we're going to do today. But before we do that, let me go ahead and turn it over to you guys. Is there anything you want to talk about from the homework or stuff we've talked about up to this point? I have a question for you. How's solving equations going? What? Doing what now? Well, that silence means one of two things. Either it's all going just fine, or we haven't even looked at it yet, or you don't even know which questions to ask. And so I'm hopeful that it's option number one. But keep working on them, plugging along. If anything comes up, definitely let me know, and we'll see what we can do to help you get it down.
Could you go over number 7 and number 13 on 9.5 practice?
7 and 13 on 9.5. Absolutely. I'll go ahead and put those on a list. If anybody else has anything, feel free to throw it in the chat box or let me know, and we'll go take a look at those as well. All right, so let me go ahead and share my screen and we'll go look at those homework sets. 7 and 13. All right, so here's number 7. We've got cosine squared w equals -9 sine of w. And we want to find all of the solutions that are between 0 and 2 pi. So remember that there are going to be more than just those solutions between 0 and 2 pi. There's probably going to be an infinite number of them. But these are just the ones that they want us to find. All right, well, let me share my whiteboard and let's see what we can do with this guy. All right, so here's our equation. We've got cosine squared equals -9 sine w. All right, so the question is, where do we begin? Well, think about what we want to do. Anytime we have a trig equation is we want to get just the trig function by itself equals a number. So then we can use the inverse trig function to find our solutions. So the fact that I see two different trig functions, sine and cosine, I really don't like that. I only want one of them. So what I'd really prefer is that these are either all sines or they're all cosines. So is there a way I can change them? Is there a way to change sines to cosines or cosines to sines? And this is where, like, if I saw your videos, I'd tell you all to go, you should start doing this. Yes, there is a way we can turn sines into cosines. In fact, there's something we learned very early on that will help us do that. How about we use the fact we've got the Pythagorean sine squared equals 1. which means I can change this cosine. I can make this 1 minus sine squared w. And so now I've got this all in terms of sine, which is much better than having sines and cosines. Since I've got multiple things with sine, I'm going to move everything to one side of the equation. So I'm just going to move everything here to the right. So this becomes sine squared w minus 9 sine w minus 1 equals 0. And now we get to use our algebra. Check this out. If I rename this, let me change sine of w into u. This is just a quadratic. It's a quadratic formula. We've got a quadratic formula we can use to solve this quadratic equation. So let's do that. Going to get negative b, so 9, plus or minus the square root of b squared, 89, 9, minus 4ac, so plus 4, divided by 2a. So we get 9 plus or minus the square root of 85, divided by 2. So that's what the u equals, which then if we go back and replace, guess it's the sine of w equals these numbers. And now that we know that, we're going to get w by using inverse sine. So I'm going to write them separately. There's the one with the plus, and here's the one with the minus. Now, those are not nice angles. We don't have anything on our chart that gives us those for sine. So now we're going to jump to the calculator. All right, so let me do the first one here. So 9 plus the square root of 85 divided by 2. And I'm going to do the inverse sine on that. And my calculator yells at me. I don't know if you can see what it says there, but it says non-real result. What now? Okay, so why did we get a non-real result? Well, take a look at the number that's on the inside there. 9 plus the square root of 85 divided by 2. So the square root of 85 is a little bit bigger than 9, right? And since that's a little bigger than, if I add 9 to that, I get something that's a little bit bigger than 18. And when I divide that by 2, I get something that's around 9. Okay, so like for this 9 plus root 85 over 2, this is around, it's around 9.11. That's way too big. Remember, sine can only be between plus or minus 1. And so that means that this is an extraneous solution. So this one right here, we're just going to cross off. Doesn't exist. If it did exist, it would be a solution, but it doesn't exist. All right, so what about the other one? Now, first of all, let's just check and see what 9 minus the square root of 85 is, or divided by 2 is. And for that one, when I do my minus, I get, so the 9 minus root 85 over 2 That's around negative 0.11. And that's totally fine. That number is between plus and minus 1. So I am going to get an answer here. So if I do the inverse sine on this, I get I don't remember how many decimal places it said I needed to be good to, but I'm going to get negative 0.109999389. I imagine that that's plenty of decimal places. All right, so that's one of the solutions. So remember when we solve equations, what we need to do once we get an answer, we need to add 2 pi n. Well, 2 pi n for sine, cosine, secant, or cosecant, pi n if it's tangent or cotangent. Because we can be coterminal, so we can keep adding or subtracting 2 pi's from that, and that will give us other values. However, there's also another set of angles where this is going to be true. Can you tell me what quadrant that's in? I know it might be hard to tell from the number, but you should be able to tell me what quadrant this angle is in. Anyone want to take a stab at it? Well, here's how you can tell. We're using inverse sine. Which quadrants does inverse sine return? It's either quadrant number 1 or quadrant number 4. That's the restriction for inverse sine and inverse tangent. So it's either quadrant 1 or 4. So with that, which quadrant is this in? Quadrant 1 or quadrant 4? Ooh, even with the 50-50, you're not sure? What's the value of sine here? The sign is negative, which means it can't be quadrant 1. It's actually in quadrant 4. So this angle is in quadrant 4. And when we add 2 pi n, we're getting in quadrant 4 every time. We're just spinning extra turns left, clockwise or counterclockwise. Okay. Real quick aside. I'm a little bit nervous that you guys aren't seeing this. Now, maybe it is you're seeing it, you're just not saying anything. I mean, that has issues of its own. But I'm more concerned that by this point, you're still not certain what quadrants we're in when you get certain plus or minus signs on your trig functions and using the inverse trig functions. If that's the case, if you're like, man, I don't know what you're talking about, you go back right now, go today, go back and get that down because we need that. We need that going forward. The more you have to think about that or try to struggle to figure it out, the harder everything going forward is going to be. Okay. So, there's not a lot you have to pay attention to. There really isn't. There are 2 restrictions on angles for the inverse trig, either quadrants 1 and 2 or 1 and 4. And the other bits of the plus and minuses, the all students take calculus totally takes care of it. So get that down. Huge advice from Bruce. okay? As someone who knows what's coming for you later, the better you know that now, the easier life's going to be later. All right, well, now why am I even talking about that? Well, it's because there's another quadrant where sine is negative. And we have to go find the corresponding angle there. So let's come back and draw a picture of our quadrants. And so we just found the quadrant 4 angle minus 0.10999. Okay, I don't know exactly where that is, but let's call that the other place where sine is negative is going to be quadrant 3. All right, so we need to find the one that's over here. All right, well, this is where we have to use our reference angles. Because if I want to find this angle, I'm going to get that by doing pi plus my reference angle. Well, my reference angle is the same as this, just positive. So that other one's going to be pi plus 0.0199389, and so on. All right, so my second choice then, and I'm going to write it down here, another possible option is going to be pi plus 0.10999,389, so on and so forth. And that gives me 3.2515865, blah, 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 plus 2 pi n. So this is the list of all of my angles. Every single solution to this equation is somewhere on this list. But now we need to get the ones specifically that they asked for, the ones between 0 and 2 pi. Okay, so if we just start thinking about spinning around from 0, the first one we run into is the orange one. So we're going to get 3.2515865, blah, blah, blah. Right, so that was that guy. And then the next one we run into is here at the green, but it's not going to be the negative. It's going to be that when I add 2 pi to it. And that's going to be 6.1731914 ... Because this guy itself is not between 0 and 2 pi, but when we add 2 pi to it, it is. Whew. All right, so there's a lot to this problem. So let's just kind of go back and sort of refresh our memory and think about what we did. So we started by using identities to get it in terms of one trig function. Do that first. Then we saw that, oh, now we have to do some algebra. It was a quadratic. So we solved the quadratic formula, use quadratic formula to get our answers. Turns out some of those were extraneous. Doesn't always happen, but it's something we have to watch out for. So we got rid of the extraneous ones. The ones that weren't extraneous, we used the inverse trig function to find an angle. But then we had to think about where else can we get an angle? Where else will quadrant? So that was this guy, the quadrant 3. So we used our reference angle stuff to find it. And then we just had to do the right add number of 2 pi's or whatever to get into the region that they wanted. And that's what this was. All right, so lots of steps, no doubt. And if you think about it, we used all kinds of stuff from trig, right? We used identities, we used reference angles, we used the inverse trig, but we also used algebra. That's going to happen when we solve equations, all right? So these are bound to have lots of different things in them. All right, so before we move to 13, is that better for number 7? And I forget who asked for that. I think it was Jack. Is that kind of what you wanted to see?
Yeah, that was perfect. Thank you.
Okay, you are welcome. All right, so let's go take a look at number 13. So we'll pop back to the homework set here. All right. So here we've got solve for cosine of 2 phi equals 4 cosine squared of phi minus 1. And just like with the other problem, they want us to find all the answers between, all the solutions between 0 and 2 pi. All right, so basically that just means at the end, we're gonna have to do the same thing that we did with this guy, which was, you know, once we've got our answers, add or subtract 2 pi's until we get all the different ones that work. All right, I'm gonna go back to the whiteboard. Let me go ahead and clear this set, start fresh. All right, so for this one, we've got 4 cosine of 2 phi equals 4 cosine squared phi minus 1. All right, so again, looking at this, I want to be able to get just the one trig function all by itself. And good news, they are both cosines. Yes, they're both cosines. But there's some bad news. One of them is cosine of phi, the other one is cosine of 2 phi. So they're not identical. Like, yes, they are the same trig function, but we got different angles in them. So I need to do the same thing we did before, which is somehow change this so that they're exactly the same trig functions. Well, what I'm going to do is I'm going to make use of the double angle identity for cosine. There are 3 forms of that, right? But one of them is, oops, not plus 1. Hold on a second here. All right, so that's the one that we get if we replace the sine squared using the Pythagorean. So I'm going to go ahead and use that guy. So that this becomes 4 times 2 cosine squared phi minus 1 equals 4 cosine squared phi minus 1. Do a little bit of algebra here. And now I'm going to move some things around so that I get 4 cosine squared phi equals 3. And then I'll divide by 4. So, oh man, this is awesome. We get cosine of phi is equal to plus or minus root 3 over 2. All right, so now we can use our inverse cosine, or if we recognize that those are values from our chart, we can get those angles. So let's start with the equals a positive root 3 over 2. So angles where that happens. All right, well, in the first quadrant, you're going to get pi over 6. I'll put plus 2 pi n. But then there's also one in the fourth quadrant. If you go way down on your chart, you get 11 pi over 6. So those are the ones that make it positive. The ones that make it negative, well, those are the quadrant 2 and 3 angles, which are 5 pi over 6, again, plus 2 pi n. And then the other one is 7 pi over 6. So there's the list of all of the solutions. So now we just want to find the ones that are between 0 and 2 pi. Well, those guys are solutions that are between 0 and 2 pi. And in fact, when we start adding 2 pi in, now we've gone too far around. So the answers are going to be pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Those are going to be angles that make these statements true. And you can check them. You can plug them back in and see, but you should get truth with all of them. All right, so here's another one where we had used an identity to make it so that the trig functions were identical. Now, obviously, the algebra we did here was different than the other one. We didn't have to use the quad. Well, depends what the structure of the equation is, right? In terms of what you have to do after you make use of the identity. All right, so better for that one, number 13.
Yeah, that was sweet. Thank you.
Okay, you're welcome. All right, this is why we care about identities, folks. Well, one of the reasons, helps us solve equations. All right. So there you go, a little bit of review of solving equations. So hopefully that will help when you're dealing with those homework sets. All right, so I'm going to go ahead and hop up to the whiteboard, and I want to start talking about how do we deal with these triangles that are not right? How do we solve them when we don't have right angles? So I'm going to hop up to the whiteboard, and I'll be right back with you. All right, so the goal for the next couple of days is going to start taking us back into the idea of trigonometry, which is measuring triangles. We want to get back to the root of this, which is finding angles, finding lengths of sides, finding areas, finding, all that kind of stuff with triangles. And right now, we are totally good with right triangles. If I give you right triangle, we know exactly how to solve it, right? So let's just think about what we need for those. So here's a generic right triangle. I'll call these angles alpha and beta. And then the sides, let's just call them A, B, and C. And so we definitely know some relationships between these that we can make use of. We've got the fact that the two angles add up to 90 degrees, or in radians, pi over 2. We also know that we've got the Pythagorean theorem, that a squared plus b squared equals c squared, right? And then we also have the 6 trig functions. I'm not going to list them all out, but those are the other things that we've got that help us relate to quantities. So I want you just to notice a couple of things. The first one, this is only angles. So that's a relationship that's true only about the angles. The second one is only the sides. And then the 6 trig functions, these are a mix of sides and angles, right? By their definition, like just think SOHCAHTOA, sine of an angle is equal to the opposite over hypotenuse, and so on. And so these are really the only tools we need when we have right triangles. If you're looking for an angle, well, if you know one of them, you can get the other using this. If you don't know any of the angles, but you know 2 of the sides, you can use one of the trig functions to find that angle, and so on. All right, so for right triangles, it's pretty easy. And it turns out we only need 2 pieces of information. And we have a couple of choices. One is if you know 2 sides, that's enough to solve the triangle, because you can use the Pythagorean theorem to find the 3rd side. And then you can pick your favorite trig function and use the inverse of it to find one of the angles, and then you're good to go. All right, so 2 sides is good enough, or 1 side and 1 angle. And in that situation, you know a side and an angle. You can use a trig function to find a 2nd side. And then once you got the 2nd side, you're good to go. And I know that we've done examples of these before, so we're not going to spend our time on this. But I did just kind of want to bring it back and let you see what it is you actually need to know in order to solve the triangle. Okay, so that's for ones that are right triangles, that have a right angle. Now, where we're going to go today, start today, is what about non-right triangles? Okay, so if they're not right triangles, so we don't have a right angle, here's just a generic one. That definitely looks not right to me. Let's go ahead and label all of the angles. And I'm going to use alpha, beta, and gamma as my angles, as my generic angles. And in order to be nice and consistent, I'm going to label my sides this way, call them A, B, and C. And I am always going to do it this way, not necessarily in clockwise order or counterclockwise, but I'm always going to do it so that the side opposite the angle has the equivalent English letter to the Greek letter. Okay, so think about the Greek alphabet goes alpha, beta, gamma. Ours goes A, B, C. So alpha and A are going to be opposite of each other. Beta and B are going to be opposite, and then C and gamma are going to be opposite. So that's how I'm always going to do it. So when we derive our formulas, this is how I'm going to derive them. Now, to be honest, I didn't look at the book. I didn't see what letter scheme they use. But this is the letter scheme I'm going to use. And the reason I'm going to do it this way instead of whatever the book may do is this is how I always think about it, which means if I don't do it this way, I'm going to slip up and I'm going to turn it into this later. And that's just going to confuse you later if I am using 2 different systems. Right? So I just know me. I know I'm going to fall back into this eventually, so we might as well just do it this way. Okay. You'll notice that I did the same thing here. Alpha and A were opposite sides, and B and beta were opposite sides. That's just how ingrained it is in me. Anyway, so this is for a non-right triangle. Now, the actual name for these are oblique triangles, but I'm going to call them wrong triangles, because if they're not right, they're wrong. And I got to amuse myself somehow. All right, so you either have a right triangle or you've got a wrong triangle. So let's talk about how we're going to solve these wrong triangles. All right, now it turns out that there are lots of different combinations of elements that you can be given to help you solve these triangles. All right, but one big difference, and this is actually a huge difference, is that we need 3 pieces of information here. So unlike the right triangles, for these, we're going to need 3 pieces of information. Okay, in reality, we actually had 3 pieces of information with right triangles. I know I said you just know 2 sides or 1 side and an angle, but the other thing that we know, even though it's not listed as something we know that one of the angles is a right angle. So there's your 3rd piece of information. But it turns out we need 3 pieces of information. All right, so what those 3 pieces are, you can know all 3 sides. So if you're told all 3 sides, you are going to be able to solve that triangle. We are going to also use a little bit of an abbreviation scheme to help us. So instead of writing it all 3 sides or whatever, we're going to write SSS as our way of knowing that this is the information that we were told. Each S stands for side. So it's side, 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 3 sides. Okay, so we can be given 3 sides. Alternatively, you could be given 2 sides and an angle. Now, there are 2 different ways that this will come about in terms of the relationship between those sides and angles. And we will see that written as either SAS, so side, angle, side, or SSA, side, side, angle. Okay, so depending upon where that angle is in relationship to the sides will be in one of these 2 cases. And we have to do each one separately. We're going to use a different technique for each one. Okay, so that's knowing 2 sides and an angle. We could also just know 1 side and 2 angles. And again, this can come about in 2 different ways. We can have angle, side, angle, or angle, angle, side. So again, it just depends where that side is in relationship to the other 2. All right, so we need to be in one of these scenarios. We either have to know all 3 sides, 2 sides and an angle, or 1 angle and 2 sides. Or sorry, 1 side and 2 angles. There's one other way you get 3 pieces of information, which would be if you know all 3 angles. But unfortunately, that doesn't actually allow you to solve a triangle. I don't know if you remember this from geometry, but if you have all 3 angles, all you know is that those 2 triangles, that they're similar, which means the lengths of the sides could be very different. So that's not actually enough to give us a unique triangle. So we can't solve angle, angle, angle. Just like over here, knowing just the 2 angles for the right triangle wasn't enough. It's the same kind of deal with the non-right triangles. All right, so the question then is, all right, given that information, how do we solve the triangle? Well, to do that, we have to develop some new relationships. And specifically, what we're going to do is we're going to develop these things called the law of sines and the law of cosines. All right, well, these are both going to be equations, theorems, laws, whatever you want to call them. The first one's just going to involve sine, and the second one's going to involve cosine. And these two tools are going to be what we're going to use for the different scenarios. Depending on which scenario we use, we're going to use a different one of the laws. All right. For example, all three sides need the law of cosines. For both of these, where you know two angles and a side, use law of sines. For the two sides in an angle, one of them's law of sines, the other one's law of cosines. So it's about 50-50. About half of them we use the law of sines, and the other ones we use the law of cosine. So with that, let me show you the law of sines. So I'm going to start with just a generic triangle, a generic wrong triangle. And let's just say this is our guy. So this will be, say, alpha. Let's call this one beta. And then the top one's going to be gamma, which means my sides are going to be A, B, and C in this way. So A is opposite alpha, B is opposite beta, and C is opposite gamma. All right, so here we go. Here's what we're going to do. We're going to draw in an altitude here, a perpendicular, so that we can actually create some right triangles. So you'll see we've got a triangle on the left and we got a triangle on the right. And this length, just for having a name, I'm going to call it H for right now. So if you look at this triangle on the left, we see that the sine of alpha is equal to H over B. Right? It's the opposite side over the hypotenuse in this little triangle. Similarly, if we look at the one on the right side, we see that the sine of beta is equal to H over A. All right, well, I've got a system of equations now. I've got two equations here, and what I want to do is I want to get rid of the H. So like on this side, I've got H is equal to B sine alpha, and this one I've got H is equal to A sine beta. I can link those together. So I get B sine alpha equals A sine beta. And I'm just going to rewrite this. So I get A over sine alpha is equal to B over sine beta. So basically all this is saying, you look at the ratio of the side and the sine of the angle opposite it, it's the same for both of these. All right. It turns out that if you were to do the same thing, but draw, say, a perpendicular from, say, this point over here on alpha down to A, you would get a similar relationship between the sides B and C. And then you could do the same thing with one from beta and C, same thing with A and C. So I'm going to add one more little piece to this, even though it didn't come from our derivation, but it's pretty easy to get. It's the exact same ratio, but with the C and the gamma. And we'll go ahead and put a box around this, because this is your law of sines. It's pretty fast to build, and it's really easy to remember. But what this does for us now is it links sides and angles. We now know how to find sides from angles and angles from sides when it's not a right triangle. But the key here is that you're always going to have an angle side pair that are opposites of each other. That's what these fractions are. Each of those fractions holds a information from an angle and side that are opposite of each other. All right, so there you go. There's the law of sine. Now, the law of sines, like I said, it's going to apply to these. It's going to apply to both of the two angles and a side. So we'll do an example of each one of those. And then the other one that it applies to is the two sides with an angle, where it's side-side angle. And I'll explain the difference between that and side angle side in just a little bit. All right, so law of sines. Know it, love it. You will love it. Especially compared to the law of cosines. This is way easier to remember, way faster to use. All right, so let me just show you. Let me just dive in and show you an example of where we would use this. So let me first give you this case. We're going to go with the angle side case. I'll do this one first. Okay, so there's an example. This would be the kind of triangle that would be an angle side. So let's say that we know that this angle is 40 degrees. This angle is 25 degrees. And this side is 8. All right, so this is two angles in one side. You can very clearly see that. And the reason that it's angle side is just imagine that we're going around this circle in a clockwise or counterclockwise direction. So like starting here, I started with an angle. The next piece of information I got is an angle. And then I got a side. So that's angle side. If we were to go the other direction, you would see it as side, angle. Well, that's just this backwards. All right, so this is angle side. Think about what it's going to have to look like for angle side angle. The side, you know, has to be between the two angles you were given. So this is angle side. Now, to help us in terms of what we're trying to solve, let me label the other pieces. So I have the two other sides. So for lack of other names, I'm just going to call them A and B. Which means then there's also this angle right here. But that one, I'm going to give it a very specific Greek letter name. And which one is it going to be? Alpha, beta, or gamma?
Alpha.
Yeah, it's going to be alpha because it's opposite A. All right, so here's basically what I need to figure out. I need to know what is A, what is B, and what is alpha. So I'm going to fill that in, and once I get those three numbers, I'm done. All right, well, before we jump to the law of sines, I'm going to go ahead and find alpha. So I'm just curious, what do you know about the angles of a triangle? Anybody remember a relationship between
Add up to 180.
Good, yeah, in terms of degrees, they add up to 180 degrees. So we know that all three of these angles have to add up to 180. So alpha plus 40 plus 25 is going to equal 180. Which tells me alpha is equal to 115. So we'll go ahead and put that here. And we are already 1/3 of the way there. All right, so easy. And in fact, I suggest you do that with either of these cases where you're given two angles. Find the third angle first, fast. You need it anyway, might as well get it so that we're done. All right, so now what about A and B? Well, let's come back to the law of sines. Now, in terms of these three, we know one of them completely. we do have a side and angle pairing, and it's these two, the 40 degrees and the side 8. Those guys are opposite of each other, so they are one of these. Obviously, the way I've named them, these are sides A and B, that makes the 8C. So we actually know this last piece, the C over sine of gamma. And that's what we're going to use to find A and B. So let's find A first. So we've got A over sine of alpha is equal to C over sine of gamma. I'm going to ignore the part with B for right now because I'm not dealing with that. So this is going to be A over the sine of 115 is equal to 8 over the sine of 40. And I can solve that for A. So we get 8 times the sine of 115 divided by the sine of 40. And notice how we know everything here. All of that, I mean, those are numbers that we know. And so this is like perfect time for us to use our calculator. So I am just going to warn you, make sure that you're in the right mode. I know I have to remind myself that anytime I'm actually solving triangles, because I always keep my calculator in radian mode, just because it's better mathematically. So I had to remind myself that when I go and do this. So just make sure you're in the right mode. But then you're just going to take 8 times the sine of 115 and divide it by the sine of 40. And I got a number 11.2797, blah, blah, blah. We'll go ahead and round it just to 2 decimal places. So this is around 11.28. All right, so side A is going to be 11.28. Done. And we use the law of sines to get it. All right, so now let's do the same thing, but find B. So we have some choices. Obviously, I want to start with the B over sine of beta. But now I can actually use either the A over sine alpha or the C over sine gamma. Because now I have A and alpha as a pair, I have both of those numbers. When I'm presented with an option like this, I always go back to the one that I didn't have to calculate. Because there's the chance that I screwed up here with my A and my alpha. But there's no way I'm going to be wrong with my C and my gamma because those were given to me. So I'm just going to use those. So I'm going to get B over the sine of 25 is equal to 8 over the sine of 40. And so you'll see here that for B, it's going to be a similar calculation, just a slightly different number there because of the fact that the beta was only 25 degrees. But again, easy enough to punch into our calculator. And this one, if I round to 2 decimal places, gives me 5.26. All right, but there you go. Now we know everything about this triangle. We know all 3 sides. We know all 3 angles. And all we needed were 2 angles and a side. All right, so there's an example of solving a triangle using the law of sines, and they really are all this easy. They're all this straightforward. It's just going to be a matter of putting our information into the right spots in the law of sines to be effective. All right, so any questions on this one before I show you the angle side angle case? No, we're good. All right. Well, then let's look at the angle side angle case. Let me just change this a little bit. So we'll do angle side angle. And here's what one of these will look like. All right, so triangle, and let's say we know that this angle right here is 32 degrees. We know that this side is length 17. And we know that this angle right here is 94 degrees. So this is angle side angle. And you'll notice now that the side we know is in between the two angles. Hence, angle side angle. Angle side angle. It's a pretty easy naming scheme. All right, well, let's label the other sides and things that we need. So I'm just going to go ahead and call this guy alpha for the sake of a name, which means I've already used, or this side then is side A, so I don't need an A. So I just need B and C, so we'll just call those B and C right there. So again, here are the three things we need. We need alpha, and then we need B, and we need C. So like before, I suggest we find alpha first. So alpha, I know that when I add to that 94 and 32, this is going to end up equaling 180. All right, so I believe that gives us 54 degrees, if I did my math properly. So I love the two angle case because I get one of the three things that I need very fast, very easily. So alpha is 54 degrees. Boom, done. All right, so now let's find B and C. So let's start with B. So we're going to use the part of the law of sines that says B over sine beta. And we need to set that equal to either the piece with the A's or the piece with the C's. And in this case, the angle side pair we know is the A's. I know alpha and A. So I'm going to use A over sine alpha. Okay, so that's going to give me B over the sine of 94 degrees is equal to 17 over the sine of 54 degrees. So B is going to equal 17 sine of 94 divided by sine of 54. All right, so crack out our calculator, let it do its magic. And again, we'll round it to 2 decimal spots. I get that B is approximately equal to 20.96. All right, so that side is going to be 20.96. It's a little bit longer. So there's B. All right, well, last thing we got to get is C, so we'll do the same thing. Let's do the C over sine of gamma. But again, I'm going to use A and sine of alpha because I'm quite confident in those numbers. Fewer cases for me to make a mistake here. So I'll get C over the sine of 32 is equal to 17 over the sine of 54. So C is 17 sine of 32 over the sine of 54. All right, and my lovely little black box here gives me 11.14. Again, rounded to 2 decimal places. And there you go. There is the third side. So I know I only showed you one example of each of these, but they're pretty straightforward. And really, it's find the third angle, then use the side angle pair that you know, set that equal to one of the others, and just go. But I want to point something out here that can help you check your solution. All right, because there is sort of an interesting thing here about the lengths of the sides. So look at our 3 sides. We had A was 17, B was 20.96, and C was 11.14. So it's pretty easy to see which of those is biggest and which is smallest, right? The biggest one was B, the smallest one was C, and A was somewhere in between them. Well, check this out. Which angle is biggest? Beta. Which angle is smallest? Gamma. And alpha is somewhere in between. And that's always the case. What the pattern is here, what we're seeing right there that I'm pointing out, is that the longest side is opposite the largest angle. And similarly, the shortest side is opposite the smallest angle. And that's always true in any triangle, even a right triangle. Even if we actually look at a right triangle, the largest angle is the right angle, and the longest side is always the hypotenuse. Just always is. Okay, so this is useful information. So what I like to do when I get my answers is I just real quick, I look at my sides and think about which one's biggest and see if that corresponds to the biggest angle. If not, I did something wrong. I got back up and tried it. Similarly, the smallest side has to be opposite, the shortest side has to be opposite the smallest. So just a little bit of a tip for you in terms of doing your check, or if you want to check your answers. Okay, so there you go. There are the two angle cases. So angle, angle side, and angle side angle. Now, the other one that the law of sines works for, if you remember from my list over there, was the side-side angle case. So let me show you an example with this. All right, so if we think about what this is telling us in terms of sides and angles, now let me just draw my generic guy here again. So this time we're going to know 2 sides. So let's say we know that this side down below here is 39. And for the sake of something else, we'll say that this guy is 25. So those are our 2 sides. And then we know an angle. And let's just say that the angle that we know is this one. And we'll go with, let's say that this is 56 degrees. No, let's make it smaller. Make it 26 degrees. Okay, so this is the situation where we have two sides in an angle, that's side-side angle. Because we know a side, another side, and an angle. The side angle side, the SAS, is going to be where the angle you know is between the two sides. So this is where the angle that we know is not between the two sides. Okay, so I'm going to be 26. All right, so far so good. So let's label the other pieces. Again, it doesn't really matter what I label them. I'll go ahead and call the side A, which means this is alpha. And then I need one more angle. So we'll go ahead and just call it beta here. So here's what we need to fill out. We need A equals, alpha equals, and beta equals. All right, so there's our information. Now, unlike the other two that we just did, I can't just immediately get the third angle because I don't know two of them. But let's think about what we do know. So first of all, why is it that we can use the law of sines? Well, I have a side and I have an angle pair, right? This 25 and this angle of 26 degrees. That's a side angle pair. That's one of the ratios that I need. So what that's going to let me do is actually use that and link up with one of the others to find the piece of information we don't know. So here's what I'm going to do first. I'm going to find beta. I'm going to go to the law of sines bit that says b over the sine of beta equals c over the sine of gamma. Because b is 39, I know that. I don't know beta, but I know c, that's 25, and gamma is 26 degrees. So notice that I know everything but beta, which means I'm going to be able to solve this. So let me move some things around here. So we get 39 times the sine of 26 is equal to 25 times the sine of beta. So we get 39 sine of 26 over 25 is equal to sine of beta. All right, so cool. What do we do then to find beta? What are we going to actually hit on our calculator to find what beta is? Think about what we were just doing last time in class. We were solving equations. That's what we're doing right here. And when it's not a nice number, we use inverse trig functions. So beta is going to equal inverse sine of 39 sine of 26 over 25. Well, let's see what my calculator gives us for that. All right, so I did some number crunching here with my calculator, and I get that beta is equal to 43. I'm just going to round this to the nearest, to 1/10 of a degree. So 43.1 degrees. Yay. All right, so there's beta. 43.1 degrees. So the law of sines actually let us find this second angle, 43.1. All right, well, now this is going to be fast. Let's get alpha next. Because I know all three angles have to add up to 180. So if I grab that real quick here, we're going to have alpha plus 43.1 plus 26 has to equal 180. Which I think is 110.9. Let me just double check that again. 69.1. Yep. All right, so alpha is 110.9 degrees. Awesome. So we're almost done. We now have all the angles. All that's left is to find A. Well, to get A, we're going to go back to the law of sines. So we've got A over sine of alpha equals, let's go back to C's because we already have those. So A over the sine of 110.9 is equal to 25 over the sine of 26. And again, we can dive into our calculator, get some numbers. And I get 53.28. And there you go. So there is a triangle which had these pieces of information. We use the law of sines first to find a second angle. Okay, right there. So you're always going to find, in this case, you're always going to find the angle opposite the second side first. We'll do that first. Then you can find the third angle using the fact they all have 180. And then find the final side using the law of sines. So that's the process always when you're in the side-side angle case. All right, so similar, right? The two angles on the side, find the third angle, then find a second side using the law of sines, and the third side using the law of sines. For this one, find a second angle, find the third angle, find the third side. That's always the process here. All right. But you're not going to like this. You're not going to like what I'm just about to tell you. This is not the only triangle with that information. There's actually a second one. What? Well, I don't know if you remember this from geometry, and some of you may never even seen this in geometry because I know that some, we kind of changed how we do math in high school and all that. But back in the day, if you took geometry where you had to try to show triangles were congruent, and that's where you use a lot of this SSS and ASA kind of stuff. Well, it turned out this one, side-side angle, was not enough information to show that two triangles were congruent. Because it's possible to have two angles with the same information, or two triangles with the same information here, to start with, that are actually different. So this one, the SSA, because of the fact that there might be another answer here, this is what we call the ambiguous case. because you can get one triangle. It's possible to get two triangles, and it's also possible to get no triangles. So given information in a side-side angle case, you don't even know for sure that you have a triangle. And if you do have a triangle, you're not assured that it's unique. There might be a second one. Yeah. And I apologize that this is the case, but it just is. And let me show you why. Let me show you why we have to watch out for it. So think about what the first step was. When we went and solved this, the very first step that we did was the one that's in black. So I'll draw a little arrow here to it. And think about how we got our answer. We were right about here, right? You got the sine of beta was all by itself. And you think about going to that next step, you used inverse sine. Now, here's where the ambiguity can happen. So think about this set of numbers right here. It's possible that that number is bigger than 1. Right? I mean, what if this side, instead of being 39, had been 1,000? I'm quite certain that that would have made this so that it was bigger than 1. Well, if we have a number that's bigger than 1 and I try to do inverse sine, I'm going to get a non-real result. Doesn't work. So that's when the no triangle situation will pop up. That's going to happen when whatever this sine is equal to is bigger than 1. All right, so we've got that possibility. There's another possibility, and that's what happened right here. Is think about it, I did my inverse sine and I got an angle of 43.1 degrees. Can't there be another angle? Like, think about this. This is a positive number. So where is sine positive? Well, sine is positive in quadrant 1 or in quadrant 2. So there's a second place where we might get exactly the same sine value. So let's look at what that quadrant 2 angle is. For the quadrant 2 angle, we have to take 180 minus the quadrant 1 angle. So if I do that, I get 136.9 degrees. So that's another angle whose sine is going to equal this. Well, that fits in this triangle. This angle is small enough that it still fits in this triangle. So while this is correct, this is only one possible triangle. So let me just write this, do this. This is triangle number 1. There's also a triangle number 2. So A equals, alpha equals, beta equals. So here's our other possible beta, 136.9 degrees. That different beta gives us a different alpha, right? Because now that alpha plus 136.9 plus 26 has to equal 180. And I believe, hold on, is it 151.62.9? I think that ends up being 17.1 degrees. Yeah. So that's 17.1 degrees. Well, that of course is going to lead us to a different A value, because even if I recycle this, my alpha is different. Now it's 17.1 degrees. So A is going to be 25 times the sine of 17.1 divided by the sine of 26. And that's going to be a different number. So let's just see real quick what that is. I get 16.77. So all of that now is triangle number 2. Okay, well, I mean, it is what it is. And this is something we have to watch out for when we're in this side-side angle case. There is the potential that there's a second triangle. So here's what you need to do. When you find that first angle, you also need to think about the one that's in the second quadrant. And that one's always going to be 180 minus what you just calculated. Okay, so let me just write this down for what you need to check. Okay, so when finding the first angle, also check 180 minus the angle. And I'm going to put here to see if it fits in the triangle. Often it's too big. Often it ends up being too large of an angle and it doesn't fit. There aren't enough degrees for it. And that's the case, you're going to be happy. There's one answer. But in this sort of situation, like we just saw, when we took 180 minus this, 136.9, that was still plenty of space. There was plenty of space in the triangle to make that work. And so that led to a second triangle. All right, so with this case, you got to be careful because there are lots of different possibilities. Now, the easiest way to remember that, of course, is that this one's ass backwards. Like literally ass spelled backwards, right? So this one's ass backwards. It's going to make you have to watch out because there may be more than one solution. All right, so there's the side-side angle case. We definitely have to pay more attention to it. But, you know, hey, it is what it is. All right, so we're going to stop here and see we're out of time. So what we're going to do on Monday, check that today is Monday. What we're going to do on Wednesday, we are going to have a quiz. We're going to have a quiz on equations, on solving trig equations. So that's going to come from, I think that's section 9.6. I don't know. I'll put a message in Canvas. But we're going to have a quiz on solving 9.5, so solving trig equations. And then I'll do another example of the side-side angle, just to kind of refresh your memory of this weird case. And then we'll develop the law of cosines, so you can see how we can use that to solve the other two scenarios, okay? So on Wednesday, God, I don't even know what day. On Wednesday, we will start at 11:40. You'll have a quiz at 11, but we'll start class at 11:40. All right. So with that, I hope you all have an awesome couple of days, and I will see you all on Wednesday. Cheers.
Thank you.